Hello friends, I'm James. So here's a typical exam question. It's often part B of a linear programming exam question, and it's actually linear programming this time. In fact, there are two types of part B questions it seems. Here's one type, and in my next video I'll do the next type. Alright, so here's the situation. We're given a graph of several lines. There's 3 lines in this graph. They define a region called a feasible region, and we're asked to maximize some formula for the points in that region. That is, which of these points, somewhere in this case a triangle, makes 30x plus 20y as big as possible. Whoa, okay, there's actually a lot of mathematics here, and it takes a long time to develop students' algebra skills to understand all the mathematics here. So let me just go through quite quickly all the mathematics we need to understand and be able to do to answer questions like this and the other type of part B question coming up. All right, here goes. Clearly, we obviously got equations of lines and graphs of lines. So students really need to understand equations of lines. Now, there's a lot in the curriculum about this, so I can't go through everything here. But we need to get to the point where students understand that every line that one graphs can actually be represented as an equation of the form some number times x plus some number times y equals some number. You know, you can do algebra, you can rearrange this, rewrite in different ways, but in the end, every equation of a line is of the form, this standard form, ax plus by equals c. So I'm going to assume that's okay, that that's understood by students. Then we also need to be able to graph equations of lines. If I give you an equation like this, make sure we can graph it. In fact, let me do that. Let me go do a couple of examples. And I'll show you how my brain thinks through these examples. For example, suppose we're given 2x minus 3y equals 6, and we're asked to graph it. Okay, grand. So we graph this thing and say, okay, I know that's the equation of a line, in which case my brain says, all I need is 2 points. Once I've got 2 points, all I have to do is get out my ruler and I can just connect them, and that would be the graph of the line. So we have to look for 2 points. Now, my brain does not like hard work, and arithmetic is hard. So often one of the easiest numbers to work with in arithmetic is the number 0. So I'm going to imagine the case when either x is 0 or y is 0, because 0 is always an easy number to work with in arithmetic. So that means I'm graphing here. I'm going to start with the graph already. Here's some axes, x and y. I want to find all the points that make this equation true. And if I look at the points where say y is 0, when y is 0, that means I must be on the x-axis. And at x equals 0, if x is 0, I must be on the y-axis. Alright, so let's think about these cases. In fact, y is 0. If y is 0, we've got 0 height, okay, somewhere along here, then 3y would be nothing. I'm just left with the equation 2x equals 6. Oh, when y is 0, x must be 3. X must be 3, y is 0. So I've now got the point 3, 0. 3, 0, right there. Beautiful, 1 point. Second point, let's now make x equal to 0. Let's make x equal to 0, it means that x is 0, I'm somewhere on the y-axis. When x is 0, that piece isn't there. Negative 3y equals 6, y must be negative 2. Y must be negative 2, something like that. Bingo, there's a second point. I've now got the point 0, negative 2. Grand, and now I've got 2 points on a line, a graph that I know is going to be a line. We can now just sketch the graph. Beautiful. Finding 2 points is all we need to do, and choose 2 easy points with zeros. Fabulous. Now let me do another example. One more example. Let's sketch a graph of, say, 30x plus 15y equals 60. That's a good one. All right, now look at the 2 cases. When x is 0, so that part disappears, and then y is 0, when that part disappears. In fact, I can do it right here. This would be great. I can do it right away. X, y. When x is 0, this part disappears. I'm left with y being 15 times 4 is 60. Y better be 4. Great, there's 1 point. When y is 0, somewhere down here, 30 times 2 is 60. Bingo. There is my graph. All the points on this line make 30x plus 15y have value 60. Lovely, lovely. Okay, but what if I change that 60? What if I made it, say, bigger to 90? Then I probably need bigger values of x and y to make that true. I guess I need some sort of line that's like bigger in some sense. I'm not sure what that means, but let's do it. When x is 0, 15 times 6 is 90. Yes, I needed a bigger value of y. Now it had to be 6. And when y is 0, 30 times 3 makes 90. I need a bigger value of x. I did need bigger values. So actually the line of 30x plus 15y equals 90 is this line. Here's all the points that give the value 90. Here's all the points that give the value 60. 30x plus 15y equals 120 will probably be bigger still. These will be all the points that give me the value 120. Here's the points that give me the value, I don't know, 500 or something. Here's all the points that give me the value 40 or something. In fact, you can see, if I keep changing this, I'll have a line that actually keeps changing position. As this starts off really big, if I start really big, it'll be over here, come down, come down, come down, come down to 90, keep getting smaller, keeps going down this way, gets really small, really small, really small, goes in the negatives. You can see that changing this value actually changes my line. It's the same line with the same slope, just actually has a different position in the plane. That is the key to linear programming. That's the theory. Because if I take the problem in this exam question that I made up, I look at this and say, oh, we're asked to maximize 30x plus 20y. We want to find a value c that makes that as big as possible. But that's the equation of a line. We know this is going to be a line. It's going to be some line. And if I do big values, if I change the values of c, it's just going to slide the line. So I want to know which value of c, what's the biggest value of c I can have that touches this region. Which of these points gives me the biggest value of c? And you think about it, here's a big value of c, not very good, no points are touching it. Here's a slightly less big value of c, not very good, no points are touching it. Oh, here's a really big value of c, here's a good value of c, and it's got 1 point touching. In fact, you can see the corner is going to be the first point that touches the line. In fact, if the line had a different slope, it might actually be the biggest value of c I could get is, coming at that corner point is going to be the one that first that meets this line with the biggest value of c. So maybe this is the corner that works. Or maybe, I don't know, maybe it comes in from a different direction somehow, and you get different values of c. The theory is, the biggest value of c, or even the smallest value of c that I could possibly get, can only ever come from the corners of a polygon. All we're doing is sliding lines, and the line's going to first hit corners. The first thing it's going to hit is a corner. It's going to hit a corner. You might be in bad luck and hit a whole edge, in which case anything works, but you know the corners are the key. So that's the method you use to solve these linear programming problems. You realize, the corners are going to be the values that give me the biggest or smallest value of c. So all I need to do then is find out, what x and y value does this point have? Put it in here and see what value of c it gives. What x and y values here? See what value of c it gives. What are the x and y values here? Put them in, see what value of c it gives. Because you know the biggest value of c is at one of these corners. So the real mathematics here in this question is, let's work out the coordinates of this point, coordinates of this point, coordinates of this point, put them in and see which gives us the biggest value of c. Okay, now let's do it. Let's do it. So this is not going to be too bad. I mean, this point here I think is actually okay. If I look at this line, it's when x is 0 for this equation. 2x plus y equals 2, x is 0, y must be 2. This is the point 0, 2. Great. This point, that's too hard. Let's do this one. So on the line, 2x plus y equals 2 again, but this time it has y equals 0 and x must be 1. X is 1, y is 0. Whoops, y is 0. It's this point, this one. It lies on this line, so it's a point that makes that equation true, and it lies on this line, so it also makes this equation true. So it's a point such that x minus 1 equals 1 is true, and 2x plus 3y equals 6 is true. Alright, so I need to find values of x and y that makes that true and that true at the same time. Okay. Alright, here's what my brain does. I see negative y here and I see positive 3y. What if I triple that first equation? Made it 3x's, take away 3y's equals 3. Still the same equation, just in disguise. And the second one is still 2x plus 3y equals 6. So if that's true and that's true, if I add them, then this must be true as well. 3x plus 2x, 5x, minus 3y plus 3y plus nothing equals 9. So if those are true, that must be true. For truth, x must be 9/5. 9/5. That's what? 18 tenths. That's 1.8. Beautiful. And what would y? Oh, sorry everyone, I just had a little technical glitch. My battery just ran out. So I'm back now, and where were we? We worked at the coordinates of this intersection point. We worked at the coordinates of this intersection point, and we're in the middle of working at the coordinates of this intersection point. We got that x was 9/5, I believe, just before the battery ran out, which means we now need to work out the y coordinate at this point. Let's see, I might use this equation, because we know that x minus y should be 1, so x is 9/5, tells me that y should be 9/5 take away 4/5, gives me 5/5, 1. Beautiful. So this point has coordinates 9/5, 4/5. 1.8, 0.8 if you prefer decimals. Okay, great. Now that's it. So the theory of linear programming says the biggest value of this linear function here right now will occur at one of these corners. So let's see what value c we get for these points, this point, and this point. Let's do it. So when x is 0 and y is 2, I get 30 times 0 plus 20 times 2. That gives me c equals 40. Okay, c equals 40. I'll do this one next because it's easier. When x is 1, y is 0, 30 times 1 plus 20 times 0, that gives me c equals 30. Not as good. Let's try this one. Does it do better than 40? Let's find out. X is 9/5. 30 times 9/5. C will be 30 times 9/5. That's 270/5. Plus 4/5 times 20 plus 80/5 plus 80/5. 80/5 gives me 350/5. That's 70. 70. Better. In fact, that's going to be the biggest value possible. The largest value of c we can get from this linear functional right here must occur right there with x equals 9/5, y equals 4/5. We have solved this linear programming problem. Whoa, a lot of work, but we did it.